Hello, this is Dr. Strickland. In this video, we will take a look at a comparison of isomers. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the more difficult things we will do together in class. Now, this is basically a chart that summarizes all of the different kinds of isomers we've talked about, because you're going to need to be able to look at a couple of structures and decide what their relationship is. So when you can identify the relationship between the structures of two molecules, you'll have a better sense of how similar their bulk properties will be in the lab. So isomers, as you know, are two different compounds that have the same molecular formula, but they're different in some respect. And in order for them to be two different compounds, they have to have at least one different physical or chemical property. Now, things like constitutional isomers that have the same molecular formula but different connectivities very often have different functional groups. Not always, but very often. And because of that, they have very different properties. You might think N-butanol and diethyl ether. This is going to have a much higher boiling point than the ether. One of them is water soluble, one not so much. So a lot of different physical and chemical properties. This one is much more flammable than that one is when you have different functional groups, and that happens with constitutional isomers. Now, stereoisomers is where we've been spending most of our time in Chapter 4. They have the same molecular formula and the same connectivity, but they differ in the three-dimensional arrangement of these structural pieces. And so now we're talking about configurational isomers and geometric isomers. Now, configurational isomers have their stereochemistry tied up in sp3 carbons. Okay, so they differ in the three-dimensional arrangement of atoms or groups of atoms at one or more asymmetric carbons. So we're talking about sp3 hybridized carbons. And are in S configurations. And we talked about enantiomers and diastereomers. We talked about meso compounds. We talked about trio and erythro pairs of enantiomers. The other kind of stereoisomers are geometric isomers. These are cis and trans, or E and Z. These are compounds that have different arrangements of structural elements at a site of rigidity, either a carbon-carbon double bond or a cycloalkane. So you might think cis and trans or E and Z. So in a cyclic structure, this would be a cis compound. In an alkene, this would be a trans compound. All right, so the two big types of configurational isomers, which is where we spent most of our time, is enantiomers and diastereomers. Enantiomers have the opposite configuration at every asymmetric carbon. Diastereomers have to have two or more asymmetric carbons, have the same configuration at least one of them, and the opposite at least one of them. Okay, so these are the definitions that you must know, and you must be able to just draw me an example of any of them. And then you also need to be able to take a look at a couple of structures and tell me what the relationships are. So, come on down here. What's the relationship between each of the following pairs of compounds? They could be identical, no relationship, constitutional isomers, geometric isomers, enantiomers, or diastereomers. No relationship is going to come up if they have different molecular formulas. That's when that happens. All right, so let's see what we've got here. First thing I'd want to check is the molecular formulas, because if they're different, then we're done at that point. So this one is C9, H, let's see, 3, 6, 9, 11, 3, 6, 9, 10, 11, 12, 14, 16, 18. Okay. And then if you come over here, 3, 6, 9, 10, 12, 14, 16, 18, still C9, H18. So we know that there is some kind of relationship. Now, are they identical? Do they have the same connectivity? No, actually they don't. So we looked at the molecular formulas. That might be, a good strategy list. Check the molecular formulas first. Second thing is to check the connectivity, because if they have the same molecular formula but the different connectivity, then they have to be constitutional isomers, and that's what we've got here, right? Because 3 of the ring carbons each have their own methyl group, but here 2 of the methyl groups are on 1 carbon. So these are constitutional isomers. And if I ask you what the relationship is, I would expect you to be able to tell me if they were constitutional isomers, because they have the same molecular formula but different connectivity. All right, so let's come on over here and see what we've got. All right, so if we did the molecular formulas, let's see what these would be. 1, 2, 3, 4, 5 carbons here, and then we'll count up the hydrogens last, and then a bromine and chlorine. So let's see, 3, 5, 6, 7, 10. And over here, 1, 2, 3, 4, C5, H, 3, 5, 6, 10, BrCl. Okay, so they have the same molecular formula. Do they have the same connectivity? It's the same stuff bonded to, since they're drawn in perspective formulas, we could just check out the 2 featured sp3 carbons. So we've got the same 3 things bonded to the left ones, the same 3 things bonded to the other one. And when you compare them, I mean, certainly this one could have been flipped over. You're just looking to see if there is a carbon that has those 3 things and a carbon that has those 3 things. So we've got the same molecular formula, the same connectivity. Now we're down to the stereochemistry. If it doesn't have a ring or a double bond, they can't be geometric isomers, but they can be configurational isomers. So let's just do this. And now you've got a list of things you can check off one at a time. Configurational would be either enantiomers or diastereomers. Okay, so let's see if what we've got here in terms of asymmetric carbons. This is an asymmetric carbon, and so is this. All right. So we could either have enantiomers or diastereomers. If we only had one asymmetric carbon, then they could be enantiomers, but not diastereomers. We would have to check to see if there was a plane that bisects the molecule to see if we had a meso compound, but we don't. And so let's see what we've got here. Let's draw in that bond, which seems to be missing. Okay. Now with this carbon here, these 2 things have been switched. So I can see that the left-hand carbon has the opposite configuration. What about over here? see. So this one is not going to be as simple. This is top priority, then this, then that. This actually is S. This one is also S. So we've got the opposite configuration here, the same configuration there. That makes them diastereomers. So let me leave you with a note here. Opposite configuration there. Same configuration there, but you'd have to work on it a bit to determine that. All right, so that's the story on the comparison of different kinds of isomers. If you have any questions about this, please send them to me.